we looked at this graphically, but now I want to study this f of x numerically. And we know that 1 is the interesting spot. So let's study what happens as we get really close to the value of x equal to 1. So I'm going to make a table of values here. I've just got a whole bunch of different x values, and then I've plotted out what the f of x values are. Because it's x plus 1, it's easy to do. I just add 1. And then the x values I'm taking, notice they're 0.9, 0.99, 0.999, and so on. These are numbers getting closer and closer and closer to the value of 1. And then if I think about what's happening to f of x, well, 1.9, 1.99, 1.999, and so on, it is getting closer and closer to the value of 2. So this scenario, we're going to use a bunch of mathematical notation. It's going to be a bit fancy. We say this big, bizarre symbol. And what we mean by it in English is that the limit of this function f of x, as my x values get really close to 1, notice that there's this 1 with a superscript of minus. That means from the left. As in, all these values are just a little bit to the left of the value of 1. That's what this minus sign here in the exponent means, all from the left. So as our x values get really close up to 1, but all from the left, the f of x values, they get really close to 2. And so we say the limit of f of x as x goes to 1 from the left is equal to 2. So that was what happened if I was looking to the left of my point 1. But what happens if we instead look to the right? So in other words, I want to take now x values are all just a little bit bigger than my value of 1. And I denote this by this 1 but with a positive in the superscript. This is now talking about going off to the right. And I read this as the limit of my function as x gets really close to 1 but from the right of it as being equal to 2. So I have a notion of the limit from the left and a limit from the right, and I can talk about a notion of the limit from both sides. In other words, I can have to have two different tables here. I've got the one table where I've got all the values a little bit to the left. I've got this other table a little bit to the right. And now I don't put any superscript at all in my fancy symbol down here. We just say the limit as x gets close to 1 without any qualification, and in either case it's going to be equal to 2. We read it, the limit of f of x as x approaches 1 is 2. So now let's investigate the same thing, but graphically. So here's our f of x, and what I wanted to do is I want to look as we get close to 1 here. And basically the idea is this, is if I get really close to 1 from either side, either from the left or from the right, that what I'm going to have is that my function values, they all get close to, what's the height here? It's this value of 2. So as I sort of get closer and closer and closer and closer to my point, maybe 0.01 from it, 0.001, 0.0001, as I get closer and closer to this point, the height of the function is getting closer to this value of 2. And so we say that the limit as x goes to 1 of f of x is 2. Exact same story as before, but now I've changed it from my f of x to my g of x, and all of my tables have changed not at all. There's no change from my f of x to my g of x in anything I've written here. Why? Well, the only difference between f and g was what happened at 1. The g was not defined at 1, but the f was. But notice what's happening with my tables. I'm putting points in that are very close to 1, but I'm never putting in 1 exactly. And so, in all of these points really close to 1, g and f are the same thing. I get this result. The g's look like they're getting close to 2 from the left. They look like they're getting close to 2 from the right. And so I will again repeat that the limit as x goes to 1 of my g of x is going to be this value of 2. And then graphically, it's this story. Remember, g of x was the one where I had this hole here. But if I'm getting really close, if I'm trying to get closer and closer and closer and closer to this particular point, well, it's true that there's no actual point there, but that the limit is still 2. The limit doesn't care what happens at the point. It only cares about what's happening as you get really close to it. And so as you get really close to this point, it sure looks like it's going to the value of 2. And so we say that it's going to be limit 2, even though the function value does not exist at this particular point. A limit still does. So in many ways, a limit is going to be an idea that's going to sort of fix problems we might have in functions like this. We talk about what the behavior looks like around a point, even if at the point it's very poorly behaved. Okay, we've got one more function to compare. That was our function h of x here. Again, h of x is exactly the same as f and exactly the same as g everywhere, except for the one point where x is equal to 1. But these tables don't have x equal to 1, so they look the same, they look like they're getting close to 2, and we say the limit of h of x as x approaches 1 is 2. And then graphically, we have a similar scenario. Let's imagine what happens if I'm going to be taking my x values and I get closer and closer and closer and closer and closer to this value right here. Now, it's true, h itself is this weird extra point that we have sticking up there. But that doesn't matter to me. The limit is an idea of what happens around a point, not at the particular point. So around this point is getting really close to that value of 2, even though at the point it's some other value. So I think what we've shown is that the limit is x goes to 1 of my f of x, limit as x goes to 1 of my g of x, and limit as x goes to 1 of my h of x, those three different functions that, while different, the limits of them were all going to be 2 at this interesting point of x equal to 1. All right, so let's try to actually come up with a notion precisely of a limit. So I'm going to define it like this. This broad collection of symbols is what I'm defining here. I'm trying to define the entire set of symbol all at once. You can think of it as sort of one single entity. And what I am defining whenever I write down a weird set of expressions like this is the following. I can make my function, my f of x, as close as I might like to this limiting value 2 in the previous case. That is, I can make my f of x as close to L as I might possibly wish just by taking the x values and making them as close as they have to be to the value of A. Close, but not equal. We don't care what happens at the point. We just want really, really, really close ones. So the idea is if I want my limit to be within some tiny number of the actual value, I have to choose x values, presumably within some tiny number of the x equal to A. Now, I should be clear that this definition that we have here is a little bit of an intuitive one. I haven't used a lot of precision. That in this particular class, we're not actually going to go into the formal definition of the limit using epsilons and deltas. If you want, you can look at chapter 2.4 of Stewart that goes into that detail and gives this sort of mathematically more rigorous definition than the bit more intuitive one that I've written down here.